Okay, welcome to the third lecture in the Introduction to Lattice Boltzmann Methods in winter 2025-2026. Today we come to the hydrodynamic limit of the BGK equation. This will be the last theory lecture before we go to the discretization and trying to solve numerical things. Today is important also for not as a standalone, just understanding the theory, but it's important to understand what we have to consider or keep in our discretization, and to what order we have to discretize the Boltzmann equation in order to solve the Navier-Stokes equation, because this is what we later want to see. Okay, there is some online problem here, but I think he'll come back later. Okay, he's coming back. So this is why I mean, it's very interesting, the hydrodynamic limit of the BGK equation. So I remind you, this is the Wagner-Cross-Krug equation, which is a simplification of the Boltzmann collision operator. So it's a simplified Boltzmann equation, which we start with, so BGK equation, which now we write without forces. So this will be the time derivative of the distribution F plus the advection of the distribution is equal to an equilibrium function that we derived from this ether theorem minus the actual distribution, and we divide this by this tau. And of course, the first question that we have to understand here is, I'm not sure we all touched on this already, but now we do it more in depth. What is tau? Did I say last time what tau is? I guess I said, yeah. So tau, this is the time scale for the return to equilibrium. So tau is a time, that's important. And the assumption is that when particles collide, yeah, they are like drunken people. When particles collide, they lose their memory. Okay, losing their memory. What does losing their memory mean? So everything that is not conserved, not a collision invariant, is kind of, after this, a random number that's drawn from a distribution, and this distribution is the equilibrium distribution. Yeah. This is how we can understand these things. So the picture that I like to draw is this. So this is a particle that is moving, and even though we do not distinguish, that's very important, we do not distinguish different particles, I still use a different number, color. But in principle, Yeah? So both particles are drawn from the same distribution, which is related to the Stoßzahlansatz, which we had some discussions in here, is this assumption of no correlation, which actually, which we need as an assumption to derive the error of time with the Esser theorem, but which is in principle not true, yeah, because after, I mean, this is true only for initial conditions, but after initial conditions, particle, after some time you meet somebody again whom you already met, yeah. So the interesting thing is, so this is a theorem, you can prove it, but the assumptions on which it is based are not reasonable. So in that sense, we don't actually know why we have an error of time. Okay, but anyway, so this is the what we as engineers usually accept somehow, yeah, because it's the correct result. So there are two particles colliding in here, and this will give this guy here another direction, so it will come to this place, and here will meet another particle, and then will continue there, where it will hit yet another particle that will yet drive it, outside. Yeah. So, and now the distances between these collisions are of course always different, yeah, because they are random events. However, we say that there is an average distance, lambda, and now we do again this assumption this lambda is somehow always the same, or it's not always the same, but this is the average, or some kind of average that we do not specify much further. So that's the lambda is the mean free path. So, and okay, between collisions. So with mean free path between collisions, we usually mean, and that's kind of important, the collision with another particle potentially of the same kind, which is different from a collision with a solid object, say, with a wall, with a boundary. Yeah? Yeah, because this, this will characterize our flow. So we come to this in a minute, yeah, but this characterizes our flow whether the probability is, so to speak, higher to meet another particle or is higher to meet the wall, right? That will completely change your behavior. Yeah? Okay, so that's the... Now I could give another lecture in this direction. Stop me. I have to, because we want to learn something else. This is the mean free path. So the particle moving here obviously has a velocity, which now I will lazily call small c, which is the mean magnitude. So it's the magnitude. Something like a root mean square, you could say. Yeah, mean magnitude of particle velocity. And then we come to this tau as the mean free time. This has nothing to do with spare time. Okay, so this is the time where the particle is spared from collision, so it's not beaten up. Yeah, it's the mean free time. So, and very simply, of course there is this relation, this linear relationship, you have lambda is equal to the velocity times the time, right? So the distance between this. And then we have specifically the speed of sound. Now, and the speed of sound actually is the root mean square velocity, yeah, of the particles. So this tau is proportional to lambda by the speed of sound. So there is okay. I must be careful. The speed of sound is not completely necessarily the same thing as the speed of the particles, which is due to particles potentially having internal degrees of freedom. Yeah. So therefore, there is a difference of order 1 that you multiply with 1.3 or something like that. Yeah. But for our purpose, and in particular in Lattice Boltzmann, where we do not consider internal degrees of freedom for particles, we can simply say that this is the speed of sound. Okay. So I have to, if you want to learn about kinetic theory, you have to go to another lecture. We do this very, very, very from eagle perspective. Yeah, no detail here. Yeah, very much simplified. Okay, so this gives us what roughly tau is, and then we look at the dimensionless numbers that would describe our problem. Numbers. So I'm guessing you're familiar with the Buckingham or pi theorem, right? Any confusion with Buckingham? So what does this mean? Does this mean no or yes? No confusion. Okay. Okay, so Buckingham or okay, people in fluid dynamics use this a lot, right? Say we have our, so this is the standard, right? We have our car. Our car has length L and is moving with velocity whatever u. Okay. So then we describe this thing here by its dimensional quantities. U, which is the velocity. Okay, it's not the, it's not the, okay, it's not important that this is the velocity of the car, yeah? It's a velocity scale, yeah? So we define one velocity and we compare that velocity to the velocity of the car, yeah? So we have a velocity scale. So let's say our velocity scale would, for example, be 1 meter per second, something like that. And then we have L, which is the length scale. So just say 1 meter. So what are now the dimensionless numbers? Okay, I do not need to explain what Buckingham theory is, yeah, and so you know there is these pi numbers, yeah, so dimensionless numbers, and you have heard some of them already, certainly, when you study fluid dynamics. So what dimensionless numbers would describe here this Boltzmann problem? Any idea? The Knudsen number, of course. Yeah, so the Knudsen number. So what is the Knudsen number? The Knudsen number is something important and funny, because you will find researchers, mathematicians that spent their entire life with CFD who have never heard about the Knudsen number, right? Yeah, so because this comes from kinetic theory. So it comes from kinetic theory because we have the lambda in it, yeah? So it's lambda compared to L, and Knudsen number. I once wrote this with T, but it's very embarrassing. So Knudsen, some Scandinavian, I believe, yeah? Okay, so you see, when I talk, this lambda is the mean free path between particles hitting. Yeah. So you see, when we look at conditions where, for example, you are very close to the wall, or you have a very thin air. Yeah. So then this mean free path gets of the order of L, right? So here the Knudsen number, this is what I meant. We are in a certain, we observe a certain behavior if the lambda is much smaller than the L. Yeah, because the L would now give you an indication how far you have to, the particle has to fly before it hits a wall, right? So in a sense, this is a comparison between how often do I hit a wall and how often do I hit a different particle, right? So the other one is more common to, I mean, the other one is a kind is the Mach number. So Mach number, Mach was this guy. So this is a kind of an insult that this appears here, because Mach was the guy who, until the end of his life, which was he died in 1910, after 5 years after the discussion was actually over. Yeah, but he defended to the rest of his life that there is no the continuum theory. So he was an enemy of the kinetic theory, yeah? And still, I mean, we love our enemies, of course, yeah, because they challenge us, but he was very much against this. And still we have his name here, yeah? Okay, now, let me see. So obviously lambda can be written as the Knudsen number times this large L. Cs can be written as the velocity of something divided by the speed of sound. Why am I doing this? Because tau is proportional to lambda divided by Cs, and this now can be written as the Knudsen number times the Mach number times our scales, yeah? And now, okay, I remind you, this L and U, yeah, this can be taken as our measurement scales, 1 meter and 1 meter per second. And say the Knudsen number and the Mach number are the things that would describe our actual problem. So how thin is the air and how fast is the car, yeah? Now you notice that this tau can be related to Knudsen times Mach, yeah? That's the message behind this. So now we do this in order to find a limiting case. So this limiting case where actually Mach would feel more familiar with. Okay, the Navier-Stokes equation historically is of course 100 years older than the Boltzmann equation. Yeah, so but it was not, is not coming there from, but we'll see how we get there. The next page. So we are interested into limiting cases. Limiting cases. So going back to our friend Mach, who believed in continuum. So question, what would we need to describe this as being in continuum? So as being in continuum would mean that that the fluid interacts, or that single particles interact more with each other than they would interact with the wall, right? So that means that L must be much larger than lambda. And that will mean that Knudsen number is going to 0. So the fluid dynamics guys, they don't need to know what Knudsen number is, because in their world, Knudsen number is always 0, okay? This is continuum, Knudsen number 0. The next thing, that because we have to finish today within one lecture, so we also assume, which is a completely different assumption, yeah, but we also assume a slow flow. And I take the liberty of saying this would lead to incompressibility. Knowing that this is not always true. So for example, you can have compressible flows that are slow. Yeah, they exist. So two examples of compressible flow that is slow. One is combustion, like even non-turbulent combustion, like a candle flame. Yeah, so there because you have this temperature difference, is flow is compressible, even though it may be relatively slow. The other thing is when you have high pressure flow driven through porous media, like you will have in natural gas things, yeah, going on, yeah. So we are not talking about this today, yeah. I just want to make sure that everything, you have to see everything in context. Nothing here is in stone, yeah. So what we assume here is u being much smaller than the speed of sound. And this would mean that the Mach number is going to 0. So also Mach is 0 now. Okay. Now we are using these assumptions to derive an incompressible continuum limit of the BGK equation. Again, the reminder, BGK, dt of f plus xi, the advection term, f equilibrium minus f in tau. So this directional derivative, yeah, so we'll always use this nomenclature that we have already used. So for the first component xi, the second component upsilon, and the third component zeta, and this into dx dy dz. Okay, is this the part where you wanted to say this is obvious? Yeah. Okay, so just for writing this out, so we have here dt. I mean, now we write out a lot to really understand what is going on, right? So we write this thing here out as xc dx f plus upsilon dy f plus zeta dzf, and I put everything on the same side, f equilibrium minus f this divided by tau equals to 0. Okay, everything on one side, so everything here together is now put into the 0 frame. Now we have introduced the countable raw moments. So we have also introduced some other moments, yeah. So the central moments and then the Hermite moments, the non-central Hermite moments and the central Hermite moments. There's an important thing to know for analysis. These simple raw moments are often required. Yeah, I have observed. Okay, I'm doing something didactical strange here. Yeah, because there's an observation that I have many of these observations. Yeah, that students after try to use. I mean, after learning from my course, they try to use central moments for doing the expansion and the analysis. And I do it here in raw moments, and there's a reason for this, because if you do it in central moments, you cannot expand to another place because the velocity in the other place is different, right? Because you know, this is a non-static frame. So if you go to your neighbor has a different frame, so you cannot simply expand this. So even though there are other moments that are useful for other things, these raw moments are useful for the analysis and will always be used in the analysis. I have a little bit the assumption that potentially people, you guys who have heard this, will potentially still do it because you forget it. Let's see. Okay, these moments are defined MABC, right? So they're integrals over the entire velocity space on F and C by the power of A, upsilon by the power of B, and theta by the power of C. And I'm very sorry that I used C now as a counter and as a, you know, we are running out of letters here, unfortunately. Yeah. So there's usually no confusion because they appear in different contexts. That's the good thing about machine learning nowadays, that we understand how we automate. That context is something that is now mathematically well defined. Previously, this was always a human thing. So instead of taking moments of this F, we can also take moments of the entire equation. Yeah? Moments of the BGK-equation. And for this it is useful that I put everything on one side, because when this thing is 0 and I integrate it with some kernel, it will always turn out to be 0 too, right? So what I'm now doing is I'm integrating this entire equation here with these kernels xi by the power of a, epsilon by the power of b, and zeta by the power c. And here comes the entire equation. dx. Okay, I'm doing a small modification here because xi is an independent variable. It does not depend on x. So it does not matter whether it is in front or behind the derivation in x, right? So I can write this xi here, f plus d epsilon d y epsilon, epsilon f plus d zeta f minus f eq minus f divided by tau, and we integrate this over xi, and all of this together is equal to 0, yeah, because we integrate over 0. So, okay, I just said this, but I write it also down. Xi, epsilon, and zeta, they are not dependent on t, x, y, and z. And this means that I can take these guys here and track them into these derivatives. Yeah? So, and what then happens also, okay, the inverse is also true. Yeah, t also does not depend on xi. This means I can also take this t and put this in front of the derivative, the integral. Yeah, because there's no, they're just independent variables. Yeah, I mean independent in the sense of the dependent. So it's coordinates, right? Yeah. So this means I can take this out. And when I take this thing here out, you see we have the definition of the moment here, right? So basically, and this I will now name as our equation 3.1. You see, I have here f, yeah? So I get dt mabc, yeah? Because this is multiplied with this here in front. However, for our derivative in x, that's also multiplied with this xi. So this xi comes together with that xi and makes this a xi by the power of a plus 1, which means here we have an ma plus 1 bc, right? And the same goes on for the one in y direction. So there's b plus 1 plus and c plus set m a b c plus 1. And back here we have only the equilibrium with nothing else, so we'll have m a b c equilibrium minus m a b c divided by tau, and all of this is equal to 0. Okay, so I hope, first of all, I hope you understand what I did, because this is something that we'll use a lot. Yeah, so that must be clear. And I also hope that you can appreciate the simplicity of these things, because because we had somebody, and I think it was invented several times independently, yeah, but say somebody had to come up with this countable with this countable version of writing down the moments. If you have moments, so because this is actually the world that I came in when we started. So we're going back 25 years or so. The idea was to give every moment a name, like, because we know them from physics. So there is momentum, there is of course energy or temperature, and then there's heat flux and so on and so on. And people were put in particular emphasis in identifying these things first and then plugging them into their equation. And then this here became very difficult, and I often on conferences and so on, I made this comparison. It's like you want to do calculus with Roman numerals. Yeah. So you can write numbers, but they are not for doing calculation with them. Yeah. So if you, instead of trying to say, so this is momentum, this is density, this is heat flux, and so on, right? If instead you use this countable format, you can actually do the calculations, because what you observe is that with every derivative in x that comes here, you will always count up one in the first index, and with every derivative in y, you'll always count up one in the second index. Yeah. So you can do directly calculation on that, which you cannot if you give everything an individual name. Yeah. So this is not by accident or something, that it is very, 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 very important concept that we need in order to do the analysis. Not everybody agrees with this, but you came to me and now you have to accept my perspective. So, because this leads us to the moment, there's still people not, one thing I have to say, the opinion on this has shifted during the last 15 years a lot, and now this is, the inventors of many of these methods had a different perspective. Yeah, I mean, it's like climbing a mountain. The first going up, they did it in a very, very complicated way, and people coming later saw, okay, you can do this here, and why don't you go, and then we modify this a little bit, and suddenly you wonder, why has this been so difficult for them actually? Because it's actually rather simple, but it's only simple. I mean, adding up numbers on paper, doing divisions on paper is only simple because somebody thought about the nomenclature that makes it simple. Yeah. Okay. Now we actually have what we call a moment chain. Because what we can do now is we can specify A, B, and C. And say we have A is equal to 0, B is equal to 0, and C is equal to 0. Yeah? So then, it's very simple. We take this guy here and put in A, B, C, right? So we have dt m0, 0, 0, plus dx m1, 0, 0, plus dy m0, 1, 0, 0, plus dz m0, 0, 1, minus m0, 0, 0, equilibrium minus m0, 0, 0, divided by tau. So now we have to identify, so now I was just bashing the old days, yeah, but we want to see what equations actually drop out. And for this, now again, we have to identify what these moments are. I mean, we already know this, but just as a reminder, m0, is the integral from minus infinity to infinity on etc. by the power of 0, upsilon by the power of 0, xi by the power of 0, sorry, and zeta by the power of 0 onto f. And all of this as 1, so it's the integral over f, and this gives us the density. Okay, I have to, the density that we compute in this way is the particle density, so it has no mass in it, yeah. So the particle density, so basically it's the number of particles that we have, yeah, in a certain volume. So I mean, we are simplifying things because actually we would have to integrate also this or specific or okay, now we take it per, no, okay, let's say we take it per volume because we have not integrated over volume. So it would be 1 over meter cube, basically, as a unit. What I'm going to say. Okay, so basically you would have to. No, what I wanted. Okay, just wanted to say that this is conserved. The particle number is conserved. So what does it mean? It's conserved. When it's conserved, then the equilibrium is equal to the moment itself. Yeah, so that we can say that m00 equilibrium is the same thing as m000, which means that this here disappears, obviously. Yeah. So, and the other guys, m100. Okay, is f the. So this is rho times the velocity in x direction. So basically it's the momentum. And you have the other guys is rho times the velocity in y direction, and this here is the velocity in w direction. Okay, so now coming back to physics. So imagine, okay, you can do all of this here without going through the countable moments, and then you see how difficult it is to make the connections. Yeah, when you use the countable moments and only plug in the physical quantities later, yeah, then it becomes simple. But still, we have to interpret this thing. So one of the interpretation. By the way, why don't you complain that this is not an equation? So this thing here and this thing here is gone, right? And when we plug the rest into it, we see that this is dt on rho plus, now we can write this again using nabla as the divergence of rho times u, which is equal to 0. Okay, so fluid dynamic guys could already identify this as the continuity equation, yeah? Okay, we are lucky continuity equation somehow drops out of the Navier-Stokes equation, out of the Boltzmann equation, out of the BGK equation, actually. Also drops out of the Boltzmann equation. Why would it also drop out of the Boltzmann equation? Why we know this directly? Yeah, the BGK is a simplification of the Boltzmann equation. However, the real Boltzmann collision operator has also conserves mass, and this is what we required, right? So in the zero moment of the full Boltzmann equation, yeah, the collision operator would drop out and will have the same thing. Yeah. So for the conserved moments, you get the same thing here. Okay, so page is finished. So moment chain, I said, we just count upwards. We can now count upwards. We're saying now we are going to A equal to 1. A equal to 1, B equal to 0, and C equal to 0. So that's the next equation that we can do. So what do we get here? So it's dtm100 plus dx m what? 200. You see, you need only a few seconds to learn this. Yeah, you cannot imagine how difficult this was before we had countable moments. I actually remember this time. So dy m110 plus dz m101. So plus minus, yeah. Okay, minus m110 minus m100 divided by tau is equal to 0. So we already know, should I actually write them down? So m100 is this momentum, momentum density actually. Yeah, I just say momentum, don't. It's not so important. This is I'm always triggered by momentum density is not conserved, but it's collision invariant. Yeah, momentum is conserved. Yeah, but okay. Momentum is conserved. So meaning that momentum density is collision invariant, meaning that this doesn't change. Yeah, meaning that this disappears. So, however, there are now things in this which we don't yet know what they are. And actually, I'll now go so far to say, okay, we don't really need to know what they are. I'm not bothering with a name now for these things, even though they have names. Yeah? But suppose we don't know about names. Yeah? We're just interested in what is actually, so what can we say about this thing here? And the funny thing is with this, so we're interested in this, right? So if we don't care what people named this thing, and we just want to have an equation for this, what we can do is we can use our moment chain. Yeah? We say that A is equal to 2, B is equal to 0, and C is equal to 0, right? Because this gives us dt m200. So we get a partial differential equation for m200, right, out of the moment chain. So when we have this, then we have, of course, here 3, 0, 0. You see why this is a chain, why this is called a chain, right? Plus dy m210 plus dz m201. And okay, I'll now take the liberty to put the thing on the other side. Yeah, and this is m200 equilibrium minus m200 divided by tau. Okay. What's the English word for Fangfrage? Trick question. Is this conserved? No, it's not. I mean, it's energy, right? Part of the energy, right? Okay, good. So this is not conserved, because the thing that's conserved is M200 plus M020 plus M002. So this is energy. I should not write energy, and this is. Okay, so if part of it is conserved, that doesn't mean that the thing itself is conserved. So how, actually, we were looking at this thing. We want to know what this thing is. Now in our BGK equation, and this is actually the point where we deviate a little bit from the Boltzmann equation, yeah, because now we have to actually look at the BGK equation, yeah. Now we can solve the entire thing for M200, yeah. This appears in the equation as a free variable, right? So we can write M200 is equal to M200 equilibrium minus tau into dt M200 plus dx M300 plus dy M210 plus dz M201. Okay, so now we know, now we have something that we can plug in the other equation, even though there could be a problem because we have it here again, okay? But let's see. Okay, let me see. So we are actually concerned with this equation up here, right? So we have another two that we don't know, this M110 and this M101. But now, since we have countable moments, I guess it's pretty simple how to write these down. So this is obviously this here minus tau. And then comes dt of what? 110 plus dx 210 plus dy 120 plus dz 111. Okay? You know, it's absolutely amazing. You had 10 minutes to learn things that took 10 years for people to figure out. Isn't it amazing? So, the other thing is so this one here is M101 equilibrium minus tau dt M101 plus dx M201 plus dy. My writing gets ugly. 111 plus dz M102, obviously. Okay, now these things have their equilibria, and then there is something here that's, okay, we could divide this moment M as equilibrium and non-equilibrium, yeah, the part that is not in the equilibrium of this, right? So when we are in equilibrium, these guys here would be gone, obviously. Yeah? So let's remind ourselves what are the equilibria of these. So M200 equilibrium. So what we have to do is we'll take this Maxwell-Boltzmann function with, so the reason, by the way, the reason why I have here the M, the mass of a particle, is because this rho is a particle density. It's not mass density. Yeah, otherwise this would go inside this row here. Yeah, so this is the mass of one particle. This times the temperature, and this by the power of 3/2 e by the power of xi minus u square. There is the particle mass divided by K Boltzmann and T, and this integrated over the kernel xi square, which gives us the second moment, the xi. And Mathematica has told me that that would be rho times K Boltzmann T divided by m plus u square rho. So then M110 equilibrium. So for this last time we spent some time how to get this. You remember? We had to normalize it. So okay, we start with normalizing it. Yeah. And then how can we write this? So obviously this gives us rho u times rho v times divided by rho and rho. And this implies that M110 equilibrium is equal to rho uv. So this we can calculate without doing the integral. You can also do the integral, yeah? But we've already proven that we don't need to. Where am I? Okay, I should probably also write that this is rho u w, okay? Okay, now we are either stuck or we go on here with the higher moment. But let's first look at this tau here and the assumptions that we made. Yeah. So tau was the Mach number times the Knudsen number times L by a capital U, and our assumptions was the system to be large. I mean large in comparison to the distance that a particle would move before it hits another particle. That's lambda. So the system is large. System is large means the Knudsen number is small and the system is slow, meaning that the Mach number is small, and this would imply that tau is 0, right?
The system is large means also L is large.
Yes, L, that's what it means. We divide by L. Knudsen is lambda divided by L.
But in this tau there is a L.
Yes, okay. Now I'm in trouble with the amount of letters that I can use. Because L so this L that we write here, we said that this L is the measure, like 1 meter. yeah, that we apply, and not, and that the size of the system is encoded in the Knudsen number, such that, I'm very sorry, I used 2 times C for something, so that the L in this here is just the scale, it's the ruler, and the L in this actually describes the size of the system. Yeah? You are right, I should have more letters. Coming from a Chinese, yeah, yes, we just have that many letters. And I think even you guys use Greek and Latin letters for writing down equations. So what I wanted to say is we'll now do the assumption. We look at the assumption that tau is equal to 0. That's not true, right? Yeah, but we just look at the assumption, okay? So that would imply that dt m100 plus dx m200 now, because only the tau is equal to 0, so everything here disappears. Yeah, so we'll have just the equilibrium here, right? Just have the equilibrium plus dy m110 equilibrium plus dz m101 equilibrium is equal to 0. Do we agree? So then we can plug the actual things. Now again, we think like a physicist and put in what we actually have here. So we have here the time derivative of rho times u plus dx rho k Boltzmann t divided by the mass of one particle plus u. This is not the same u as this, right? So this is a big u, yeah? U square rho, I have just so many letters, plus dy u v rho plus dz u w rho, all of this equal to 0. Okay, now these operators, I sometimes wrote them in front. So these operators act on rho times u, which means we have to use the product rule in order to see what they. Okay, we can use the product rule to rewrite all of this, and what I'm going to do is I use my observation that u appears everywhere here, right? So I first take the part where I can write u in front, dt rho plus u dx rho u plus u dy rho v plus u dz rho w. So this is where I could drag u out of this, plus the inverse where I put rho, where I can drag rho out of this, so rho dt u plus rho u. Okay, now I take this as a unit, yeah, and put this in front. Rho times u dx on u plus rho v dy on u plus rho w dz on u, the other kind of brackets. And then there is one part that I've not taken care of, and this part I'll take the liberty to put it on the other side, dx rho k Boltzmann t divided by m. Now the things that I put in these brackets, this is basically equal to u dt rho plus divergence of rho on the velocity, which we have already identified to be 0. Yeah? So that means the entire thing here disappears. And we have only the other one left. Which means we can write the equation that is left as rho dtu plus rho u onto, okay, that's the vector and that's not the vector. Yeah, that's correct, because it's only the x component, thank you, minus dx rho k Boltzmann divided by m and t. So, is this already familiar? Should be familiar. So we have something that's called an ideal gas law, where we have a pressure times a volume. Pressure times a volume is k Boltzmann times t, and this volume, because we have particle density, not mass density, is 1 over rho. Yeah? So basically P is equal to rho k Boltzmann t. And this k Boltzmann t, by the way, is also the speed of sound squared. Yeah? It's the kinetic energy of a single particle, or the single degree of freedom. So, which means we can rewrite this in order to make it even more familiar as rho dtu plus rho u onto u is equal to 1 over. This thing here comes here because we have not in this row we don't have the mass. Yeah, so we have actually particle density. This is why we need a mass of a particle here, because this is inside, mass is inside the pressure. So what's the name of this equation? Euler equation, right. Everybody familiar with the Euler equation? I guess, yeah. So this is the Euler equation. Okay, so first step is we get the Euler equation out of the Boltzmann equation. It's already an achievement, but what we wanted to see is whether we get the Navier-Stokes equation out of the Euler. Because the Euler equation is, yeah, kind of useful, but not as useful as the Navier-Stokes equation. I guess you agree. So the reason that already we're in the discussion is that tau is actually not 0. Yeah? So this was the assumption, tau equals to 0. Yeah? Infinitely large system. But it's not true. It's not infinitely large. So this is not true. So what happens if this is not true? So if it's not true, we get a different equation, and this different equation is rho times, okay, so most of this is still true, yeah, just we get additional terms on top of them, right? They previously disappeared. But we still have rho dtu plus rho u dot u is equal to 1 minus 1 over m dxp. And then we get all this non-equilibrium terms that previously we have deleted. So we'll get here tau, and dx. And now comes the non-equilibrium part for m2, 0, 0. Yeah? And we know, if I may go upward, we know what this is. We know these three equations. Yeah? So we just take these three equations, which we can easily generate, as we saw, and write them down here. Yeah, we take the x derivative of this here, dtm. So this is now the non-equilibrium part of m200, right? Plus dx, so comes m300 plus dy m210 plus dz m201. So this was part 1. I take the liberty to write tau again in order to, for me to better organize this. Dy, now comes the non-equilibrium part of m110. So it's dt m110 dx. Are you following me? M what? 210 plus dy 120 plus dz 111. And lastly, we get the one for for m101, which is dx m201 plus dy m111 plus dz m102, right? Okay, so I'm going to call this here the part that we added. Now I'm going to call this S to give it a name, right? So now you see we run into a problem because all of these things now depend yet again on other moments. And this leads us to something that you know, or you probably know if you are familiar with, in particular, turbulence modeling. Are you familiar with turbulence modeling? You probably. You guys should, so you heard about it, right? And in turbulence modeling, you heard about the so-called closure problem, right? So actually, I can't prove it, but I believe it's actually exactly the same thing. It is the same thing, yeah, coming from two different directions. So you have this because we are describing the same thing, yeah. We are here on Navier-Stokes level, yeah. We are describing exactly the same thing. We have a closure problem in the Navier-Stokes equation when we try to Reynolds average them, and we have a closure problem if we try to derive an equation for fluid dynamics from the Boltzmann equation itself. Because whenever, so what does closure mean? The closure means you have an equation in which there is a missing variable, and for this missing variable you have to get a new equation for in which you will have a next missing variable, and this goes on indefinitely, right? So we need the next order of moments is required. So why not doing it like artificial intelligence? Just try out, go on and brute force, yeah? So say we want to know what is M300. Now comes in handy the BGK collision operator that we assume, because all the moments, the linear operation, all the moments relax, all the moments have the same tau, yeah? So we can obviously write this is M300 equilibrium minus tau, same tau because there's only one. And here dt M300 plus dx M400 plus dy M310 plus dz M301. You're following? Easy, right? Then we also have M210 is M210 equilibrium minus tau dt M210 plus dx M310 plus dy M220 plus dz M211, and M111 is your homework, of course, yeah? I mean, I guess you know now how this works. Okay, so what we see, we need order 4. So yet we have the next order of moments. And I was a little bit ahead of myself. Now we write this down. We get an infinite hierarchy. Okay, we have an infinite hierarchy. And of course, we just have a few more minutes left or so, or 20 minutes left actually. Maybe take a little longer, but we want to stop this. How to stop this? Anybody, any ideas how we could stop this? Suggestions? Yeah, okay. Modeling, yeah, so, okay, so this is what comes out of the runs idea, yeah? But how modeling? So what, I mean, modeling is too generic, yeah? You actually would have to say, how would you model this?
I think in the turbulent flow, it's the closure problem was solved by modeling, right?
Is solved by who?
By modeling.
By modeling, okay.
Epsilon model.
Okay, if you call this a solution, I mean, it is closed by, so basically you have to, yes, so of course we will also model it, yeah, but you have to give a specification. By the way, we are still, in principle, we are still on a very solid path here, relatively speaking, because we only want to have the Navier-Stokes equation and not the Navier-Stokes equation to all, I mean, we are not necessarily talking about turbulence yet, yeah? So the thing that we kind of model, or don't really model, is again looking at our tau. Said that for the Navier-Stokes equation, tau is still small, yeah? This thing is small, but it's not 0. So what does this mean? Our model is yet another assumption which is not as stringent as the one that we had before. We assume that tau being larger than 0, but tau square, or everything tau cube, and so on, they will be negligible. Yeah? So this is our assumption. And now what you see then is that this M300 basically becomes M300 equilibrium plus something of the order of tau, right? Because this is the thing that is of the order of tau. Yeah? So we'll keep this, and the equilibrium we compute by taking again, what is this, rho divided by 2 pi k Boltzmann t. This is something that I don't know by heart. E by the power of xi minus u the square m divided by 2k Boltzmann t. Now we multiply this with xi to the cube and integrate this over xi. And this, because there's no tau in this, I take tau outside. First order now, right? So, again, I'll like to plug these things into Mathematica. That gives me rho u 3k Boltzmann t divided by m plus u square plus something of order tau. So M210. So what is the equilibrium of M210? You should actually now know this already by the logic. Yeah. So what will this be? Rho kBt
divided by m times rho u or rho v
times,
rho v.
no, there cannot be two rho. Okay, no, only one rho by v, okay?
Okay, yeah.
And then I would have written this in a different way, but this is still, if there's still something missing, but so far we are good. So you need to know there's M200, right? So M200 is rho k Boltzmann t by m plus plus u square, also rho now because and then this times v. Okay, I would have written this with brackets, but now you get it this way. Yeah? So plus, because this is equilibrium and the non-equilibrium is of order tau. M111 is what? We always have a rho u v w, very well, plus something of order tau. Okay, so in order to get done with this, I introduce two unnecessary simplifications. Yeah, that simply that's okay. These. So they are not necessary. So I will now assume that t is a constant. Yeah, we don't bother with t. And we also assume low velocity, meaning that everything that's velocity to the cube is 0, also u square times v is also 0. So in particular, this is not necessary. Yeah, if we keep these things inside, what we can do is we can use the chain rule and isolate these things and identify that they will all be multiplied with the continuity equation and then all drop out. It's a good exercise for you, yeah? It's a good exercise for you trying this out, yeah? So I just want to get to an end, and there I just say, okay, let's drop these terms, yeah? This gives us the same result. So having this result and having what we previously called S, yeah, so the part that comes to the Euler equation. So this S, again, I write it down here again, S tau dx into dt. Now I plug all the moments inside here. So this is the the second. Okay, we are talking first about this here, yeah? So now this is the equilibrium of the second order moment, and this is K Boltzmann T divided by M and rho, and then comes what plus, wait, there is, did I write this in my, okay, there is an assumption that I've forgotten to write down because we would have to. So we assume in our assumption here that dt u square, yeah, this is also 0. This is something that I've now dropped out. Okay, maybe I should. You know, we should actually include all of this. Just the computation would get more than the last few minutes that we have. Yeah. So because there would be a u. See, I was potentially not careful preparing this here because this here is also an assumption that we need. Sorry, I just go on. M3 U, this is now the third moment, 3U K Boltzmann T divided by M and rho, dy V K Boltzmann T divided by M rho plus dz W KBT divided by M rho, and all of this goes with an O delta of something of delta tau. Yeah, and okay, since now I'm messing up with this, yeah, I encourage you to include this thing here and do not assume these things here and see that you can actually make them drop out, but I will not demonstrate this here. Yeah. So this was the first part, and then we have the part tau dy dt okay, so there is no dt here because this second moment is M is again M110, yeah. So the same thing will here apply again, yeah. So there is no dt, yeah. So we'll get dx. We start from dx, V k Boltzmann T divided by m and rho, and also there is something dropping out because there is the term v times u square is also dropping. V times, okay, let's be a little bit more accurate. Yeah, so it's u square times v, yeah? Yeah, so this will drop out because it's third order. Or we ignore it because it's third order. It's not actually dropping out. Plus, somebody told me that I'm always trying to explain everything. Now I'm myself getting confused when I'm trying to do a simplification, because actually doing simplifications is very dangerous, because you're in danger of dropping out one term and not the others, and these two would cancel. Yeah. That's here the problem. Actually, you avoid this if you write everything. Yeah. dy. Okay, I'm going to use my script now. This is kt divided by m rho, and here comes another term of order tau. And by the way, I'm going to call this thing here as Sx, and I'm going to call this thing here as Sy, and then there comes the Z, which is the thing that comes from M101. Yeah, so again, there is nothing in T, but we have dx w k Boltzmann T divided by m and rho plus the Z now, u k Boltzmann T divided by m rho plus o order tau, and this we call then SZ. Okay, now we are going to we look at this Sx here first. And for this, we recall the continuity, which we would also have used if we had all the terms inside to see that we can eliminate a lot. And we put this in Sx. So what we can identify here is that we have the time derivative of rho. Here we have a time derivative of u rho, but we also have 3 in front of this. And here we have xu, and here we have yv, and here we have zw, and we have k Boltzmann T by m everywhere, right? And we have a dx in front of all of that. So we can identify something that's dx onto k Boltzmann T by m. I said we assume T is constant. This is why I'm just moving it around. Now we have dt rho plus divergence of rho u. Now I made here a terrible mistake. Okay, now that would be a 0, right? But this is not what we have up here. What we have up here is 3 of them. So we can take one of the 3. We can take one of the 3 out and combine them with the others in order to see that this will disappear, right? So this means that we can write this Sx as being tau. Now the second derivative of 2u k Boltzmann T rho divided by m plus, now comes something of order tau square. And tau square, we decided that we will ignore this, right? So having this, we can combine this with the other part and rewrite our S again as tau k Boltzmann T divided by M to dx x u rho plus. So what I'm going to do now is I'm taking one of these. There are two left. I'm taking one of these, write it here, and then I see that I have here a dy on u with k Boltzmann T in front that I put here in front. So I can also write dy u rho and for the z part I can do the same thing because I have dz and I have dz times on u here again. So I'll write dz u rho. So okay, I'll have now I basically have taken this guy and I've taken this guy. So there's something left, obviously, right? So this means we have to write tau k Boltzmann T divided by M, and now we get okay, from what is left, we have one of these left, we have this left, and we have this left. And what we recognize that all of them have a dx in front. So we start with saying we have a dx here. This goes into dx. So the first one is u rho. The second one is dy v rho plus dz w rho. And all of this comes with things that are of theta square, such that we can write this entire S as tau k Boltzmann T divided by M into, so this is the Laplace operator, yeah? Laplace u rho. So looking further into this, we would discover that we can also move the rho, but this should not now be our concern. Plus tau k Boltzmann T divided by M. We have left with dx, and here we have obviously the divergence of u times rho. So now this is the part that is added to our Euler equation. Yeah. So we get here rho times rho dt u plus rho u times nabla u is equal to minus 1 minus m dx p plus tau k Boltzmann T divided by m. So, and I was a little bit quick and inaccurate. This is why we still have the rho in here, and I know some mathematicians that will jump on my head for this still being here and say this is not the right Navier-Stokes equation. Yeah, okay, don't worry. Yeah, so we are pretty close. dx divergence u rho. Okay, so this thing is reminding my sloppiness with the rho, yeah, but this is the Navier-Stokes equation. And if we are in an incompressible flow, this divergence thing here would also be disregarded. The last thing that we still have to do is to identify that this here is the viscosity, and okay, the m would have to be mixed with the rho, yeah. So this k Boltzmann T is actually is actually cs squared, the speed of sound square, such that we can write the kinematic viscosity nu as tau being tau times the speed of sound squared. Yeah? So this is in the Navier-Stokes equation, and actually you can, and this is actually the how Einstein first discovered from theory, basically, from this calculation, how big a mean free this mean free time is, and from this what is the mean free path, and from this you can then get a rough estimate how large are these particles actually, right? So actually it is from this kind of calculation, not exactly this calculation, but it's from this kind of calculation that it was first discovered how large molecules actually are. Now we have electron microscope, and now we can see them and measure them in other ways. But the first time this was discovered was actually by Einstein reasoning about the Brownian motion and comparing this to the diffusion coefficient, and from the diffusion coefficient, which is easy to measure, and the speed of sound, which is easy to measure, we can determine the mean free time, and then together again with the speed of sound, we can determine the mean free powers. Yeah, and then from viscosity, we know from the measurement of viscosity and speed of sound, we know what is it's not really the size of the particles, but it's, you know, related to the size of the particles. So we get an idea how large they are. Yeah, and if you plug in the numbers for air, for viscosity, you'll turn out with 60 nanometers, which is of course much larger than an air molecule, but it's the distance that an air molecule can travel. So, yeah, thank you for staying with me. I will now stop the recording.